Our previous video dealt with concavity, and this video will deal with something directly related to it, points of inflection. A point of inflection basically is where the concavity changes. Our definition also talks about the fact that it has to have a tangent line. Most of the time, I'd say 99% of the time, you don't even need to worry about that. There might be a few special cases where we need to look at that part of the definition, but mainly it's just where the concavity changes. So we're going to look at 5 examples here, and I'm just going to ask you to try and think about where the points of inflection might be. So maybe just try that on your own for a second. Pause the video, try to figure out where they would be, and then we'll come back. And if you're keeping score at home, this is approximately where your points of inflection would be. Just as we look at a couple here, right here it's concave down, now it's concave up. Here it's always concave up, so there are none. Here it's concave up, switching to concave down, concave up, concave down, concave up. This is concave up, but then right about here it does change. This is probably the toughest one. Here it becomes concave down, and then here it's curved again to be concave up. And so you guys will look at lots of examples of these. These will get much easier as time goes on. So, points of inflection. They occur when the graph changes concavity. So what do we know about concavity? Well, based on our previous lesson, the graph's going to change concavity when the second derivative changes signs. It goes from positive to negative or negative to positive. So that's really what we're going to be interested in here, is when we say where's a point of inflection, just like where's it concave up or concave down, we're going to look at the second derivative. We want to know when the second derivative equals 0 or does not exist. Now, this note is very important. Just kind of showing where things equal 0 is not good enough to show that it's a point of inflection. You actually need to show that the sign changes, so we need to do a little bit more testing. I want you to think back to the first derivative test where we found critical points. Critical points, all you had to do was show that the first derivative equaled 0 or did not exist, and it was a critical point. But now for points of inflection, you have to do a little bit more than that with the second derivative. You actually need to show that signs change. So the actual example here will be pretty straightforward. Find the points of inflection for this function. You need to find the first derivative so that we can eventually get to the second derivative, set it equal to 0, and then test signs for a little bit. So here we go. First derivative would be, let's see, we have negative 2x cubed, so that would be negative 6x squared. And then we'd have a plus 12x. If you notice, I believe this is from a previous example. So then the second derivative would equal negative 12x plus 12. And I want to know where this thing will equal 0, or where it's undefined. This will never be undefined because we're never going to divide by 0. And we can go through and solve this algebraically. You guys can think through it a little bit. But this will equal 0 when x equals 1. So that is that x value. That's the potential spot where we might have a point of inflection. And so to finish this up, or at least to get us started, I need to make a sign chart for the second derivative. Okay, so I'm going to plug in a value. Maybe I'll plug in 0 over here for that side into the second derivative. If I plug a 0 into the second derivative, this will be a positive answer. And then maybe I'll plug in a positive 2 to test that side. If I plug a positive 2 into the second derivative, I get a negative value now. And so because the second derivative does change signs, I have a point of inflection. Now I want to be a little careful with how I write this out, just like I've done with all my other tests. So here's how I would write things out. I'd say something like this. Since the second derivative is greater than 0 from, and this says from negative infinity to 1, and the second derivative is less than 0 from 1 to infinity. So first of all, I'm naming the thing I'm talking about. I'm actually saying the second derivative of g. And then these are a range of x values. So since I've said that it changes signs, Now the second derivative changes signs. There has to be a point of inflection at x equals 1 based on the definition. And a lot of times, because they're asking about a point of inflection, a point has an x and a y value, they might even expect you to come up with the coordinates. So if I know that my x value is 1, if I plug it back into the original equation, calculate all that out, I'm going to get an answer of 1 as well. So the actual point where this happens is 1, comma 1. 1 to the right, 1 up, and that's actually my point of inflection. A lot of times we say POI for point of inflection. I'd probably say don't use that sort of terminology in your final answer here, but if we're just in general talking about points of inflection, you could use POI.